Hello everyone, my name is Yu, and this is a joint work with Shaddin and David at USC. So the central question we study in this talk is the following. That is democracy more effective when the candidates for office are of the people? And by of the people, we just mean they're drawn from the population, say uniformly at random. We work with the assumption that the candidates and the voters are embedded in a common metric space. This has a long history, and you also have just seen it in the previous talk. So we define the cost of a candidate to be his average distance to all the voters. Recently, work in the EC community studied the distortion of social choice rules and mechanisms. And here we define the distortion of the election to be the cost of the winner over the cost of the optimal alternative. So let me start with a very simple but canonical example, which you've already seen in the last talk as well. So here we have an election between two candidates, a left-wing candidate colored blue and a right-wing candidate colored green. The distance between them is 2. And the voter population is given by the red arrows. So we have nearly half of the voter being left-wing, and the rest are central but slightly biased towards the right. Let's look at the social cost of these two candidates. So the blue candidate has a cost of roughly half, and the green candidate has cost roughly 3 times that much. So the distortion of this election, the green candidate wins by a small margin. So the distortion of this election is 3. So we stare at this example, and we identified what we think is a consequence for such a high distortion in this example. That is, this green candidate, this right-wing candidate, he's not of the people. There's no voter population. In this example, there's no voter population that's at that position. In fact, in this example, had we drawn two candidates randomly from the voter population, we would always elect the socially better candidate. Why? There are 2 cases. Either we draw 2 candidates from the same position, then their social cost is exactly the same, so the distortion is always 1. Or we draw one from the left and one from the center, in which case the centrist is going to win, and that's optimal. Right? So one way to look at our paper is asking, for this example, draw the candidate from the population, help improve the situation. So does this intuition hold in general? We're going to see it does. So it brings us back to our central question, which is, does the social welfare improve when we draw candidates IID from the population voters? In this paper, we focus on the most basic and fundamental setting. That is, we have 2 candidates and a majority vote election. From this point on, I'm going to assume that the candidates are always drawn from some distribution over the metric space. And then we're going to examine 2 cases. One is that this distribution is arbitrary. It has nothing to do with the voter population. We call it non-representative. The other case is when this distribution is uniform over the population of voters, where we call it representative. So this table summarizes our results. So first we show for when the metric space is a line, you get a bound of 1.17, and that is tight. And for general metric space, we show a lower bound of 1.5 and an upper bound slightly better than 2. While in the non-representative case, we give a tight bound of 2 for both the line and general metric. So the takeaway message of our work is that voting becomes more effective when you have representative candidates. This can be seen from comparing the left column of this table to the right column. The number becomes smaller when the candidates are representative. And 2 is that the exact improvement of when you have representative candidates depends on the complexity of the metric space. Because even though we didn't pin down the exact answer for the metric space, we know that it drops more for the line than arbitrary metric space. Okay. Now I'm going to show you the technical part, how we prove these results. First, let me start with line metric and representative candidates. I'm going to start with some structural results about voting on the line. So what I mean by that is, let's say I give you a voter population in the metric space, and then I draw two candidates from the voter population, and I ask you, between the two of them, which one's socially better, and which one's going to win the election? Okay? What if I draw the other two? So the structural result gives you a quicker way to answer this question, like who wins and who's better. Okay? So it turns out the median voter plays a very important role for the voting on the line. The first lemma says if you draw two candidates, then the one closer to the median is going to win the election. Okay, why is that? In this case, everyone, including the median, and everyone on the right side of the median is going to vote for X, and that's more than half of the population. This actually also holds true when you have candidates on different sides of the median. The most important thing is once you get the median, then you get more than half of the population. Okay? So the first lemma tells you about the voting ordering on the line. And the second lemma tells you about the social cost ordering. Turns out in this case, we can only give you ordering if you draw two candidates on the same side of the median. And the one closer to the median is going to have a smaller social cost. The intuition behind that is more than half of the population needs to first get to X before they can get to Y. So if you combine these two lemmas, you get a very important structural result. That is, whenever you draw two candidates from the same side, the majority voting actually elects the better candidate on the line. So we use these structural results, and as well as many other structural results that I did not show you, to prove a tight bound for voting on the line. And the way we do that is we show, given any distribution with support potentially larger than 3, there is a series of operations we can reduce the support size to 3 while preserving the distortion at the same time. It's worth noting that when we're shifting the probabilities, we actually cannot guarantee that between any pair of the candidate, the distortion does not decrease. We use a more global argument for that to happen. Just to give you a feel of what those operations are, it essentially boils down to identify two critical voter, X star and Y star, one on each side of the median, and then carefully move probability mass while preserving the ratio until they are the only ones left. So then you end up with a distribution of support 3. And once we get down to support 3, we can optimize the probability and locations of those 3 points, and you get the worst case of roughly 1.17 as claimed. This concludes the proof for the line metric. Now I'm going to move to the general metric space with representative candidates. So let me first show you a lower bound of 1.5, so what we conjecture to be the worst case instance in general metric space. So what happens here is this is a voter distribution. This is a voter population over the metric space. So you have nearly half of the voter sitting on the left-hand side in this cluster. And you have these little dots, smaller dots, represents smaller fraction of voters sort of well spread on the right-hand side. So what happens here is whenever we draw one candidate from the left and one from the right-hand side, the number on the line represents the distance between them. So the little dots on the right-hand side are actually slightly closer to each other than they are to the left ball. So they're going to vote for each other when this green candidate is drawn. And the green candidate is going to win the election. You can we can compute the social costs of these two candidates, and see that when this happens, we get a distortion of 2. Since we draw one from each side with probability half, when that happens, the distortion is 2. When we draw 2 candidates from the same side, they have the same social cost. The distortion is 1. So the expected distortion is 1.5, as claimed. Right. But we cannot show a tight upper bound for this case. What we can show is something that's strictly better than 2. And the way we show that is we identify some special structure of your instance, as long as your instance has expected distortion sufficiently close to 2. So recall that this is an example that you get the worst case distortion of 3. We show that when your distortion is sufficiently close to 2, you must have a pair of candidates that their distortion is very close to 3. When that happens, your instance is going to look very close to this one, except that we cannot, because it's not actually 3, it's close to 3. Instead of saying you have nearly half the voter on the blue candidate, we can only say that you have roughly, say, 47% of the voter concentrated in a small ball near the blue candidate, and the remaining remaining voter are roughly equidistant to the 2 candidates. And if you recall the lower bound, we just see the 1.5 instance. This actually looks very close to that instance, except there are roughly 6% of the voter population missing that we don't know where they are. It turns out they can cause enough trouble for us to show something that's actually pretty far from 1.5, but still strictly better than 2. Okay? So now finally, let me show you a tight bound of 2 for the non-representative case. This is the worst case example. So the voter population is the same as in the distortion 3 example, but now the candidate distribution is designed in a way that you draw 2 candidates from different sides with the highest probability, which happens with probability half. So when that happens, you get a distortion of 3. When that doesn't happen, you get 1. So the expected distortion is 2. And the way we show that is, Elliot already showed in his paper that even though a majority voting can elect a worse candidate, the candidate cannot be too much worse. So the critical idea for this proof is you can actually ignore the metric space information and just look at the cost of the candidate. So with probability X, you're going to draw a candidate of cost Y. And then you optimize that distribution, and this turns out this relaxation is tight, and that's going to give you an upper bound of 2. Okay. Now let me quickly summarize our result. Actually, I will not show you the table again. So Abraham Lincoln said in Gettysburg Address that the government of the people, by the people, for the people, shall never perish from the earth. And in Lincoln's words, the result in this paper can be expressed as for 2 candidates and a majority rule election, a government by the people is better for the people if it is also of the people. So open questions, the most immediate technical open question is we don't know the exact worst case distortion for the general metric and non-representative case. We conjecture it's 1.5. And then one could also ask the question of how gracefully does the distortion degrade when we have something between representative and non-representative. Say, what's a function of the worst case distortion as, say, the normalized, as the function as the Earth mover distance between the voter distribution and the candidate distribution. And one could also ask a question of, let's say, instead of having a line, I have a Euclidean space of small dimension, then what is the worst case distortion in that case? And besides these 3 questions that's directly related to this table in some sense, everything in this paper are dealing with 2 candidates. So it remains open what happens when you have more than 2 candidates. And with that, I will conclude. Thank you for your time.